It's time for quantum mechanics basics. Free your mind. Lab coat fashion. White socks and sandals. Perhaps even the blasphemous peanut butter sandwich with one slice of white and one slice of wheat. Let's start by talking about the physics of the couch. There's an unspoken rule in common society: 2 guys to a couch. If my buddy's sitting here, you can bet I'm sitting right here. And if someone sits in the middle, I'm gone to get some nachos. That's what we call Pauli exclusion. Guys are like fermions. Fermions are a type of particle in the universe that just needs its own space. Electrons, protons, neutrons, all of these things tend to pile up at energy levels because the most convenient locations got taken up by 2 guys. There's other types of particles in the universe called bosons. Things like photons, or even certain collections of fermions that have an even number, behave in a different way. If I got 3 girls on a couch, and the girl in the middle gets off and moves over, perhaps the girl on the end slides over. "So tell me about Ben," she says. You see, girls are like bosons. They don't need so much personal space. They don't mind sharing the same wave function, as it were. When I apply a potential change, you can see that the water flows. This is like a metal. In metals, there are more energy levels available than there are electrons to fill them. And so what happens when I apply a voltage, the electrons just simply slosh to find the next available energy state. This is a conductor. This dish is completely full of water. When I tilt it, nothing happens. The water doesn't move because there's nowhere for it to move. This is like an insulator. So when all the energy levels are filled in a material, no current will flow. So this is like glass, and this is like a metal. But what would happen if there was an energy level just above this one, low enough that we could actually sometimes get water up in that top level? Well, that's a semiconductor. Let's see how that works. This is a semiconductor. Electrons delocalize in the valence band, which is completely full, and electrons don't flow. But at a slightly higher energy is something we call the conduction band. This one is completely empty. However, we can put impurities inside of semiconductors that allow them to conduct, and this is how it works. I'll bring this closer so you can see. If you notice at the bottom, there's a bubble. And as I tip this, the bubble moves. What's happening there is that there are impurities in a semiconductor that gobble up electrons and create a deficiency of electrons in that valence band, so that when I tip it this way, the water moves down, but the bubble moves up. Likewise, if I provide impurities in the conduction band that dope it with excess electrons, those electrons can run freely in the conduction band. So this is sort of a model of how a semiconductor works. There's electrons that run around freely up here, and there's holes or bubbles that move around freely in the other material. Now, I can specifically dope these materials such that there's only holes or there's only electrons. And those are called p-type and n-type semiconductors. And when you put them together, what you get is something called a diode. Imagine a theater where now I have a completely full lower deck except for one empty seat. If I have an earthquake and everyone shifts, the empty seat moves the opposite direction. So I have a row of people and everyone moves to the right. The hole, or the empty chair, moves to the left. In the upper deck, imagine that I have people now, where I have a p-type semiconductor with extra seats, and I have an upper deck where there's just extra people. If now I have an earthquake and tip this thing, the people from the upper deck will fall into the empty seats that are moving up as people slide down. So empty seats slide this way, people slide this way, and in the middle, what we have is recombination. So as the people fall, they scream and they emit energy, and that's how a light-emitting diode works. You forward bias it, electrons move from the n-type material to the p-type material. As they drop in energy, they emit light that we can see. And depending on the height of that gap, we see red, green, or blue emission from the LEDs. That's how the LEDs work, and it's all based on this distance between the conduction band and the valence band. Well, what determines that distance? What it has to do with is the electron wavelength. And let me draw something for you right here. So electrons don't want to be where the nuclei are. So their wave function will tend to go to 0 wherever there's an atom. So you see, if the atoms are closer, the electron's wave function is smaller. But the electron could also have a different wavelength, a wave function, with twice the period. So you can imagine the green one is like the electrons down here in the valence band, and the higher frequency, higher energy electrons, these are like the conduction band. So if I go from a material with large electrons where the nuclei are spaced far apart, to a material with small electrons where they're spaced closely together, the energy levels go up and the energy difference goes up. This energy gap is really a function of how small the atoms are and how closely they can come together. If we go to a material that's got large atoms, like say gallium arsenide, then it's got a band gap, an energy gap here, that's out in the red to infrared range. However, as we shrink those materials, if we go to aluminum arsenide, suddenly the aluminum is much smaller than the gallium, it's higher up on the periodic table, and these atoms can fit more closely together. Suddenly that energy gap becomes wider and wider, and now we can emit blue light, or even UV light. And that, moving to the ability to move to aluminum arsenide or aluminum gallium arsenide, or even aluminum nitride, is really what provided the revolution in LEDs that allowed us to have blue LEDs that could pump phosphors to create a white light. So the wavelength of electrons delocalized in these valence and conduction bands determines that energy gap. And that energy gap is what gives us semiconductors. So diodes are the basis of transistors, which is where computers come from. So if you can just imagine the electrons in the conduction and valence band, you'll do well to understand a lot of the things that go on in the world around us, from LEDs to computers. Thanks for tuning in.